So, this is a decreasing sequence of numbers, and this can go up to minus infinity. However, whatever is the graph, whether it has a negative cycle or a positive cycle, it really does not matter what kind of graph it is. The delta sequence is always finite. Delta 0 v is greater than or equal to delta 1 v is greater than or equal to delta n minus 1 v, and it stops here, and after that all values are equal. That is because, as we have seen already, the maximum number of edges in any path is just n minus 1. That is the reason why this will not extend any further. You will have only equal values, it will not descend beyond this point. So, we write like this, equal to delta n v equal to delta n plus 1 v, and so on. For all of them it is equal. How are alpha values and delta values are related? Our goal is the delta values. So, we will see how alphas and deltas are related. Since every path is a walk, since every path is a walk, it is clear that P K V is a subset of W K V. A path that has got at most k edges is also a walk that has got at most k edges. Therefore, every element of P K is an element of W K. W K may have more elements. So, because of this, the bigger sets will have smaller minimum value, right. Therefore, alpha k v is less than or equal to delta k v. All right. So, alpha and delta are related this way. There is another interesting fact, is always greater if G has no negative cycle, then alpha k v is equal to delta k v. That is because if a graph has no negative cycle, every shortest walk will indeed be a shortest walk, a path. If G has no negative cycles, every, and also we will avoid zero cycle, in the sense zero cycle edges can be simply removed without changing the values. Okay. Every shortest walk is indeed a shortest path. Okay. This can be easily proved by contradiction. If the shortest walk has a repetition or as a cycle, that can be removed and the weight can be further reduced. Let us say S to V is a cycle, this is a walk. I can remove this cycle of edges and still have a walk from S to V, and that walk will have a smaller weight. That is because I am removing a cycle. I am assuming that G has no zero cycle, no negative cycle. So, cycle, if there is any, they are all positive. So, I am reducing by a positive quantity, and that will be a contradiction to the minimality. So, if the shortest walk has a cycle, it can be reduced and then you can find a shorter walk, and that is not possible. That is the reason why shortest walk cannot contain any cycles. That means it is indeed a path. No repetition of vertices or edges, therefore, that is the reason why we have this equality. Okay. This is very interesting, alpha kV equal to delta kV. Now, we will take a closer look at the definition of alpha k for k equal to 0 and v equal to s, and those edge cases are to be sorted out. Okay. So, what can we say about alpha k s? What do you mean by that? S to S there is a walk, that means it is a closed walk. Okay. This is a closed walk. And what can we say about delta k s? This is a cycle, closed path. This is okay. Now, the case when k is 0, what can we say about delta 0 s? How do we define this? Less than or equal to 0 edges, no edges. From S to S, okay, without any edges. It is possible for you to go, just do not move out of S, right. And therefore, since there is a possibility, except that you are not using any edge or anything, okay. So, the weight is assumed to be 0, delta 0 s is 0. Same for alpha 0 s is set to 0. What can we say about alpha k v when k equal to 0, that is alpha 0 v. So, from S to V you have to go with 0 edges. It is not possible. A walk does not exist with 0 edges, right. There is no way with 0 edges you can go from S to V where V is not equal to S, right. So, alpha 0 V equal to infinity, since a walk from S to V, V not equal to S, it is some other. How will you go with 0 edges? There is no way. Therefore, such a path does not exist, since a walk from with 0 edges does not exist. Whenever something does not exist, path or walk we said to be similarly delta 0 v equal to infinity. So, this remember these boundary cases. So, in sum alpha 0 s equal to 0, alpha 0 v equal to infinity for V not equal to S. Similarly, delta 0 S equal to 0, delta 0 V equal to infinity for V not equal to S. If G has no negative cycles, then alpha 0 V equal to delta 0 V. This will be greater than or equal to alpha 1 V, but alpha 1 will be equal to delta 1 V, and this will be greater than or equal to alpha n minus 1 V, which is equal to delta n minus 1 V for every vertex, and we stop with this. There is no need to proceed further. If you consider those further elements, they will all be equal to these elements, and delta n minus 1 V we know is a delta V. Therefore, alpha n minus 1 V equal to delta n minus 1 V equal to delta V. This is the important observation, and we will see how we are going to use this. Since alpha n minus 1 equal to delta V, and notice that alpha is a decreasing sequence. Therefore, I have a decreasing sequence leading to my answer. In other words, something can be made smaller and smaller in n minus 1 stages, I get the answer. So, if I have a method of improvement which is using alpha I to compute alpha I plus 1, I can apply that procedure again and again. I will start with alpha 0, compute alpha 1. I apply the same procedure, start from alpha 1 and obtain alpha 2. Apply the same procedure again on alpha 2 and get alpha 3. In this way, I can keep on computing the values, one smaller than the other or one solution better than the other, and in n minus 1 stages I am going to hit the answer that I am looking for. So, we have to look into the technical details of how alpha I plus 1 and alpha I are related. If I could explicitly derive the relation, then I can devise a computational process which will use that relation and obtain the values. Okay. Fortunately, we have the alpha values satisfying the equations much like the Belman equation. Okay. In other words, let us recall what the Belman equations are. The Belman equations are delta V is delta V is less than or equal to delta U plus weight of UV, and there is an edge such that delta V equal to delta U plus weight of UV. This is for all UV. There exists UV satisfying this condition. Together we got delta V equal to minimum of delta U plus weight of UV. We are going to get a similar relation. So, these are called Belman equations for bounded walks for minimum weight bounded walks. Here I am not considering all walks. This is a minimum across all paths delta value. I am now focusing on alpha, but again alpha with respect to a k. We will show that theorem alpha I plus 1 v is less than or equal to alpha I v less than or equal to alpha I u plus weight of u v. For all edge u v this will be true, okay. This is true for all edge u v in E. But there is an edge, there exists an edge u v such that alpha I plus 1 v is exactly equal to alpha I u plus weight of u v. These two together imply that alpha I plus 1 v is equal to minimum over all edges u v such that delta u plus weight of u v. Consider all the incoming edges to v. Each incoming edge to v is going to define one value. Take the minimum over all, you are getting this identical to the Belman equation for weights of the shortest paths. These are the weights of the shortest walk among the bounded walks, walks with bounded length. While the Belman equation for shortest path weights, they have circular dependency, non-linearity and so on. There is nothing like that here. Left hand side has got n values to be computed, but they are depending on a completely different set of n values, okay. So if I have, oh I am sorry, this is not delta I, this is alpha I. Right hand side has got alpha I values, left hand side has got alpha I plus 1 values. So I have a vector of values alpha I s, alpha I of other vertices, okay. There is a vector of values. Using this I can obtain the another vector of values alpha I plus 1 s, alpha I plus 1 . So if I have one array of values, I can compute another array of values without any clash, cyclic dependence and other thing. There is a formula. What are all the values in this array I have to consult to construct one element of the next array. In order to compute alpha I plus 1 of a particular vertex, okay, what are all the alpha I values I would need, okay. For example, if I have u1, u2, u3, these are all the incoming edges to v, then in order to compute alpha I plus 1 v, I need alpha I s, alpha I u1 I need, alpha I u2 I need, alpha I u3 I need, similarly alpha I u4, okay, u3 is enough, let us So, in order to compute this value, I need this one and this one, which are all available. Okay. So, I am assuming that alpha I array of values available, then the array is indexed by vertices. The array is indexed by vertices. For example, if the vertex at V is V1, V2, etc. Vn, then I have alpha I yes, let us say V1 is yes, then alpha I V1, alpha I V2, then I will have alpha I Vn. All these values I assume I have, then I can compute alpha I plus 1 V1, alpha I plus 1 V2, alpha I plus 1 Vn. These n values I can compute using these n values. Okay. How do you compute? Here is the formula. Okay. Alpha I plus 1 V is minimum of alpha I u plus W u v. Weight of the edge is there and alpha I values are there in one array. Use the values in that array to build this array, and all alpha I values are smaller than all alpha I plus 1 values are smaller than alpha I values. Therefore, this is an improvement. Compute the array of values alpha I plus 1 by using the array of values alpha I, this array, and this is called improvement step or improvement procedure. I have a computation, set of computation I will do, and if you look into definition, this theorem, it is saying that alpha I plus 1 is minimum among these values. Okay. We have already seen this being a subset. Alpha I plus 1 V could be alpha I V or minimum of this, right. Therefore, if the shortest walk in W I plus 1 V has less than or equal to I edges, it will be a shortest walk even in W I V. Hence, in this case alpha I plus 1 V is equal to alpha I V. If it has got exactly I plus 1 edges, because it can have up to I plus 1 edges. Now, assume that the shortest walk has exactly I plus 1 edges. So, I have a shortest walk, this has got a S to V, this is the last edge in the walk, this S to V walk has got I plus 1 edges, Therefore, this part will have I edges, this part will have I edges. We will use a simple notation. Let W S V be a shortest walk from S to V with I plus 1 edges. Then W S V can be written as W S U plus U V. W S U plus U V. The portion of the walk from S to U and the edge U V. We claim this is a shortest walk. We claim that this is the shortest walk. If this is not the shortest walk, this is called cut and paste argument. Okay? The style, the proof style is known as cut and paste argument. If W S U is not a shortest walk, let W dash S U be a shortest walk. Okay. I will draw W dash also in the next. S to U V, this is W S U, W dash might be something like this. This is W dash, this is W. Weight of W dash S U is less than weight of W S U, right. That is because this is not the shortest, W is not the shortest, W dash is the shortest. W dash is the shortest walk with W dash has less than or equal to I edges. Now I can cut and paste. I can remove W S U, include W dash. So from S you go through W dash and go to V. So weight of W dash plus U V is equal to weight of W dash plus weight of U V, but this is strictly less than weight of W plus weight of U V, okay, weight of W dash ends at U, W S U plus weight of U V, which is equal to weight of W S V, which is equal to alpha, this is the shortest path, right. So its length, its weight is going to be alpha I plus 1 V. This is a contradiction. I have another walk with a smaller weight, okay. Its length is also less than or equal to I plus 1 and its weight is strictly smaller. It is a contradiction. This contradicts the minimality of W. Okay. We have started with the shortest walk, W is the shortest walk, and W dash plus UV is a shorter walk, not possible. Shorter than the shortest is not possible. This contradicts the minimality of W. Okay. W dash has got less than or equal to I edges, W dash plus UV is less than or equal to I plus 1 edges. Here is a walk with less than or equal to I plus 1 edges and whose weight is smaller than alpha I plus 1 V, not possible. Therefore, such a W dash cannot exist. This implies such a W dash cannot exist, implying W SU is a shortest walk and it has less than or equal to I edges. This implies weight of WSU equal to alpha IU, and this implies weight of WSU which is equal to alpha I plus 1 V, which is equal to weight of WSU plus UV, which is equal to WSU we have shown is alpha IU plus weight of UV. That means we have shown that alpha I plus 1 V is equal to alpha IU plus weight of UV for some edge UV. It is very easy to show that alpha I plus 1 V is less than or equal to alpha IU plus weight of UV. That is because you take any W S to U, this is W, and it has got less than or equal to I edges extended by V, add the edge UV. This is a walk, the total thing is a walk with less than or equal to I plus 1 edges. Therefore, the weight of that walk must be larger than or equal to alpha I plus 1 V. What is alpha I plus 1 V? That is the smallest weight. This is some walk, therefore its weight will be larger. That means alpha I plus 1 V is less than or equal to, W has got alpha IU, the edge you have added is weight of UV, and this proves the second part. Okay. So, take any shortest walk, add, you are going to get a walk with less than or equal to I plus 1 edges. That is an arbitrary walk. The weight of an arbitrary walk must be larger than or equal to weight of the minimum or the shortest walk. Therefore, this follows. Okay. Hence, we have proved that alpha I plus 1 V is equal to minimum over all UV such that alpha IU plus weight of UV. Therefore, no circular dependency, and once I have an alpha I array of values, I can compute alpha I plus 1 array of values. I know alpha 0 array of values, alpha 0 S equal to 0, alpha 0 V equal to infinity. Therefore, we know alpha 0 array of values. Using this, obtain alpha 1 array of values. Using this, you obtain, so you go through n minus 1 stages, okay. You go through n minus 1 stages, alpha array to alpha 1 array to alpha n minus 1 array. So, stop after n minus 1 improvement steps. You would have got alpha n minus 1 V. We know that since the graph has no negative cycle, this is in fact delta n minus 1 V. We also know that delta n minus 1 V is in fact delta V. Therefore, you can output the alpha n minus 1 V values. Very simple algorithm, iterative procedure. Getting this delta V from Belman equation was hard. Getting these values using the Belman like equations on bounded walk lengths, walk weights, we are able to get an iterative algorithm. It is improving the weights of the walk, and finally it converges to the answer we are looking for. Though we are working in the class of walks, the shortest walk being shortest path, we are able to show that the convergence of that sequence is same as the convergence of the sequence that we want. Note that this is not true for arbitrary graph. For arbitrary graph, if you apply this kind of a improvement step, you are not going to end up with shortest path weights. You will get some values, but they will not be shortest path weights. However, if G has no negative cycle or 0 cycle, applying n minus 1 improvement steps lead to the answer we are looking for. This is the key idea behind Belman and Ford algorithm. We will take a detailed look at Belman and Ford algorithm in our next session. Thank you.